We're back for part 3 of the little lecture for 9.1.2 for Pre-Calc. And we were doing problem 9-15 and 9-16, and now we're on 9-23. And it says a square matrix has the same number of rows and columns. Which of the following properties are true for square matrices A, B, and C of the same dimensions? So like if you had a 2x2 and another 2x2, or a 3x3 and a 3x3. Be sure to explain why or why not. Give examples to justify your reasoning. So is matrix addition commutative? So I know that these aren't, I just want to use some, reuse some matrices that we already have, just to make the video a little shorter. But if I add two matrices together, does it matter which one's in front? Like here's an example of where I added some together. If I would have put the MS on the left and the MF on the right, it wouldn't matter that, I mean, I'm still going to add the numbers. I'd still add 182 plus 166 is still 348. So we're going to say that matrix addition is commutative. Is matrix addition associative? That is, if I go A plus B and then add C to it, is that the same as if I add B plus C to A? Well, it turns out that's true also. I don't know if we have an example of that. I don't see an example of that, but you could try. You could make 3 matrices and add them together different ways, and you'll find out that yes, it is associative. And do matrices satisfy a distributive property? Yes, because we just did that here. So we had M times F plus M times S. Like we did the big matrix times little f plus a big matrix times little s. And then we added them together, and we got the same exact thing as if we just add the f and s together first and then multiply by the big matrix. And you can hopefully see that that looks distributive, and it's true. It's true for the square matrices. So matrices satisfy the distributive property. Is matrix multiplication commutative? Does A times B equal B times A? Well, it's not, and I think I'll go ahead and show that right now. So let's make some matrices. A. I like to call it, I'll just go 1, 2, 3, 4, and I'm going to multiply it by B. I'm just thinking of some handy numbers, okay? That says 1, 2, 3, 4, 5, 6, 7, 8. So I want to multiply them together. So I'm going to get, this is a 2 by 2, and this is another 2 by 2. And so I'm going to end up with a 2 by 2 matrix for my product matrix. And we'll call this matrix A times B. And I'm going to, so this little, I'm going to have 4 little components in here, and this component, the top left, this is going to be row 1, column 1. So I'm going to use row 1 and column 1, just like we were doing earlier. So I'm going to go 1 times 5 plus 2 times 7. So 5 plus 14. So 5 plus 14, I think that gives me a 19. And then this is row 1, column 2. So I need to multiply row 1 with column 2. This is column 2. So 1 times 6 is 6, plus 2 times 8 is 16. So 6 plus 16. Is it 22? Yeah, I think it's 22. Okay, and then, so what's this one? This is row 2, column 1. So on my row matrix, I'm going to do row 2 by column 1. So 3 times 5 is 15, plus 7 times 4 is 28. What's 15 plus 28? Is it 43? Okay, and then this is row 2, column 2. So I'm going to use row 2 and column 2. 3 times 6 is 18. 8 times 4 is 32. I got 50. Okay, so I got a matrix when I multiplied A by B. Now I'm going to multiply B by A, and you're going to be surprised. So now remember B was 5, 6, 7, 8. And A was 1, 2, 3, 4. Top left is row 1, column 1. So I'm going to multiply row 1 by column 1. 5 times 1 is 5, plus 6 times 3 is 18. So 18. Well, it's already messed up. It's already not the same. It's not the same. I mean, I could keep going. This one would be row 1, column 2. That's 10 plus 24. That's 34. That didn't work. This is 7 plus 24. I think that's 31. And then this would be 14 plus 32. 46. Anyway, you can clearly see, I didn't need to keep going, you can clearly see that A times B didn't end up being B times A. So that is the very long answer to letter D. Is matrix multiplication commutative? No, it is not commutative. Is matrix multiplication associative? Yes. I don't feel like I have time to do, I'm going to let you try it. You go A times, or, you can just make up some little matrices, and make up 3 matrices, and multiply them, multiply the first 2 together, and then take the product and multiply it by the third one. And then do it again, but multiply the second 2 together, and multiply that by the first one, and see if you get the same thing. You will. So yes, it is associative. And then the next thing we learned today was that there's an identity matrix, and it always starts with a 1 in the upper left, and it always goes diagonal, and all the other entries are zeros. So if I multiply this by any 2 by 2 matrix, because this is a 2 by 2, I'm going to get the same exact thing. Like if I go multiply 1, 2, 3, 4, that's just my made up matrix. If I multiply that by an identity matrix, I'm going to get, I got a 2 by 2 and a 2 by 2, so I'm going to get a 2 by 2. This is row 1, column 1. So 1 times 1 is 1, but 2 times 0 is 0. So 1 plus 0 is 1. Okay, now this is row 1, column 2. So 1 times 0 is 0. 2 times 1 is 2. Okay, here's row 2, column 1. 3 times 1 is 3. 4 times 0 is 0. So that's 3 plus 0. That's just 3. This one here is going to be 3 times 0 plus 4 times 1. 3 times 0, that's 0, that's 4. Didn't I end up, when I multiplied by this matrix, didn't I end up with the same thing I started with? And I'll just tell you that if I would have put this matrix, if I would have switched the order and put the identity matrix here, it still would have, I still would have come out with 1, 2, 3, 4. Because the identity matrix, no matter which way you do it, like, it's not commutative, but it's whatever it multiplies, you're going to get out the product's gonna be what you started with. And then this very last one says, if you have an M by N and a P by Q, so let's go. This is a M by N and this one's a P by Q. Then I want you to know that if I multiply them together, I'm only allowed to multiply them together if these two match. So N has to equal P. And then the dimensions of the matrix that comes out, the product matrix, will be an M by Q matrix. And I am out of time, so that's all I got for you.